Now, why is that? So does anybody want to, I mean, whoever knows what a vector is, tell me what a vector is. Anybody who doesn't know what a vector is, venture a guess, type it in the chat, raise your hand, do whatever. So I'll give like 30 seconds of thought as to what a vector is, and then feel free to give your answers. Okay. 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 I'm starting to see some answers. Okay. So some of you guys are saying a dynamic array or a list of numbers. That's a little bit more abstract. We're going to think of vectors in the more physical way because physics is physical. So yes, you can think of vectors in terms of what's called their components, but we'll get to that later. So fundamentally speaking, a vector has a magnitude and a direction, as people have said. So a vector has a magnitude and a direction. So does anybody want to like represent this geometrically on the board? So feel free to annotate on this screen what a, oh my God, annotate like good, awesome. It's an arrow. Cool. So awesome. Oh, we've got cool. We've got awesome.
I feel like
okay, so Arib.
Go a little bit more basic for now.
More basic. Okay, so let's stick to this, just the arrow. So if we have an arrow, or let me make it red so that y'all can tell that it's different. Here's red. So the magnitude of this vector is just the length of this vector, represented as the norm of R, or the absolute value of R. If our vector is R, this is our magnitude. And then our direction is, as Arib has already demonstrated, this angle theta. Now, the reason that we use direction, like when it comes to using direction, we need to orient that direction with respect to something, right? We can't just say, you know, it's facing like, I don't know, left or right. Left of what, right of what? So that's why for vectors, it's standard that, all right, I think that's enough drawing. It's standard that we orient based on the x-axis. So this angle will go counterclockwise with respect to the x-axis, and that's our direction. So does anybody want to tell me why I put absolute value of R for the magnitude?
It's like the distance from the origin of the where you're placing the vector. An absolute value is kind of and like on a normal number line, it would be the distance from 0.
Exactly. Yeah, I've said absolute value. Ignore that. I mean norm, magnitude, same symbol. Basically, that just means the distance from 0. Because if I draw a vector, a different vector in this direction, that's technically negative, because if I do this, oh, and this is like -3, for example, and this is, you know, -2, this magnitude, the length of that thing is still positive, which is why we use this, which is why when we say square root of something, you know, square root of, you know, this plus this squared plus this squared, this refers to a positive value. Square root in this instance is always going to be positive, and square root in physics is always going to be positive. You might have learned, you know, that, you know, square root could yield positive and negative solutions. That's for math. You know, in math, we say x squared equals 3 has 2 solutions, 3 and -3. But the square, 3 and -3. X squared equals 2 has √2 and minus √2. But in physics, the square root of 2 is the positive value. The same way the square root of 4 equals 2. It doesn't equal minus 2 in physics. So that's just something you should remember in terms of math for physics. Okay, so we've covered what a basic, yeah, that's a little bit more complicated. So let's just keep it at that. So we've covered basically what a vector is. So now, the problem is not all vectors, if I draw a bunch of vectors in space and they're all, you know, just differently situated, I can't really do anything with them. Why can't I do anything with them?
They don't have the same origin.
They don't have the same origin, exactly. They're not going from anywhere. The reason that vectors are so powerful in mathematics and in physics is because we can move them around. Because this vector, or it's not letting me draw for some reason, this vector, it's still not letting me draw. This vector, good, awesome. If I move it to the left, to the right, up and down, the magnitude's not changing, right? The magnitude stays the exact same. I haven't stretched it. And the direction also stays the same because I haven't rotated it. So I can move this vector, I can translate it wherever you'd like. Harib, I am not going to name every physicist right now, but anyway, you can move this vector left, right, up, down, you can translate it, and the vector will be the exact same vector. The vector will be congruent, it won't change. Which means we can, in order to do something, move all of these vectors so that they have the same starting point, the same origin, so that they come out of the same point. Move this one here. I'm doing my best to approximate. Now we can do something with them. You know, now we can talk about these vectors with respect to each other because now we've got angles between them. Now we can measure different things. We can take what's called their dot product, their cross product, all that crazy stuff. We can add them, we can subtract them because they all come from the same origin. So even though it's technically possible to have vectors just all spread out in space, when we as physicists deal with vectors, we deal with them coming from one point. That point is usually the origin because it's the easiest. It's 0, 0. Because then the magnitudes of what's called the components are just, you know, that location. So we've discussed now what fundamentally a vector is. We now know and have established that we can, you know, move these vectors around. As long as they're coming from the same point, we can do stuff with them. So now let's talk about what we can do with vectors. We can add them, we can subtract them. Let's talk about that. So I don't know how to add a page. So Alvin, if you want to add a page, go ahead.
I got it.
Awesome. So now let's talk about vector operations, or vector properties and operations. I have horrendous handwriting, so pardon me if you can't read this. Divgrad curl. Yes, that's a good vector calculus book. But anyway. Okay. Yeah. So vectors, we've established already, have a magnitude. This is the magnitude. If this is the x-axis, this is their direction. It's always counterclockwise with respect to the x-axis, with respect to the positive x-axis. So this is plus x. With respect to positive x-axis, this angle always goes this way. So we know the magnitude, we know the direction. Cool. Every single vector can be split up into what's called its components. So this is when Jeremy and the other people said that vectors are collections of numbers, this is what they're referring to. They're referring to the mathematical representation of a vector, its components. So what do we mean by components? Let's draw a bigger version of, let's draw a bigger graph of our vector. So here is our vector, R. Here's the positive x-axis. Here's its direction, theta. Now, again, mathematically speaking, we can define it in what's called, in terms of what's called its components. In other words, we can construct a triangle and we can deal with these legs instead of the hypotenuse. In fact, we can express the direction and the magnitude in terms of purely the components. So this is what's called the vertical component, because it's opposite the directional angle and perpendicular to the horizontal. So this is what we call r sub y. And that's not a vector, my bad. And then this is our, yeah, I'm aware. This is our horizontal component, r sub x. So now we can write everything about the vector in terms of anything else. So if we have the magnitude and the direction, we can now compute rx and ry in terms of that. If we know rx and ry, we can compute the magnitude and the direction in terms of those. Would anybody like to, here, let's try this little exercise. So write out the components rx and ry in terms of theta and r. This is our r. And write out theta and r in terms of rx and ry. So anybody like to volunteer, write it out?
Steven, why did you erase that?
Because he forgot the arctangent.
Ah.
Oh, I probably gave it away. Okay, awesome. So we've filled them all out. So now let's go over it. So Rx, we know that the cosine of the angle, if we're dealing with a right triangle, is the adjacent over the hypotenuse. So the adjacent over the hypotenuse in this case is Rx. Yes, arctan is inverse tangent. So Rx over R is cosine of theta. So awesome. Cosine theta equals Rx over R. Now we want just Rx. So we multiply both sides by R. So R cosine theta equals Rx. Now what does this mean? This means the horizontal component is directly proportional to the cosine of the angle, which means the greater the angle, the greater the incline, what happens to the cosine of an angle as the angle increases from 0 to 90?
Inverse tangent is not cotangent.
Yeah, that's the reciprocal of tangent.
Yeah.
So anybody want to tell me, like, what happens to the cosine of an angle as the angle goes from 0 to 90?
Repeat that.
As an angle increases from 0 degrees to 90 degrees, so from flat to vertical,
Yeah.
what happens to the cosine of the angle?
Decreases.
It decreases, exactly. It goes to 0, exactly. Which means, what will happen to the horizontal component of our vector as the angle increases? Exactly. The horizontal component will decrease, which is incidentally exactly what happens when, if you start standing up, your shadow will appear smaller. So anyway, if the sun moves and the angle between you and the sun increases, your shadow will appear smaller and smaller, which is why when the sun's directly overhead, you see no shadow. Because your shadow is basically the horizontal component of you as a vector. So when the sun is over here, basically flat, your shadow is very, very long. As it rises, your shadow gets shorter and shorter and shorter until directly above you, you see no shadow. Yeah, exactly, Arib. If the sun is directly overhead. Now, because it's very rare that the sun is directly above you, you'll always see a little bit of shadow. But if the sun is directly above you, you will see absolutely no shadow. And the exact same thing works for the vertical component, except what is it proportional to instead of the cosine of the angle? What do we have? Well, it's written right here, but anybody just want to shout it out? Everyone alive? I know it's 5 p.m. on a Tuesday. Yeah, sine, the sine of the angle, exactly. So now what does this mean conceptually? If the angle starts increasing from 0 to 90, what's going to happen to the sine of the angle? It's going to increase. And if the sine of the angle increases, what happens to the vertical component? Well, no, the vertical component will increase. Yeah, exactly. The vertical component will increase. Awesome. Perfect. So, yeah, that's basically components. That's what we often, we in a lot of cases, when it comes to working with physics problems, working with, for example, on an incline, for example, if I have like some sort of object on an incline, like, and I want to measure forces on it, we're going to cover all this later, but just very simply, we will describe forces in terms of vectors. Because this is inclined, the forces acting on this object will act in at a different angle with respect to what it considers the ground. You know, gravity always acts downwards towards the center of the earth, so gravity will point directly down, but directly down is at an incline, is at an angle with respect to the ground for this object, which is why these components help. Components also help for extreme cases. You know, you're going to see in a lot of cases on either physics problems on your tests or in F equals ma that there'll either be some sort of thing times cosine theta or something times sine theta. And a good way to check whether it's cosine or sine is to see how this object changes, how this magnitude or value will change as you increase the angle to extreme points. So what are two extremes? The extreme is either it's flat or it's vertical. And if you look at it being flat or vertical, you can guess. So for example, like if you are talking about friction on a surface, right? And you're trying to measure what friction is proportional to, well, think about extreme angles. If the angle is 0, sure, just give me a second to read. But if the angle is 0, the object is not going to move. So the object will be stationary. So that means that the forces of friction must be at their maximum. But if you go to an extreme case and it's vertical, the object is just going to fall. So you know that it's then proportional to the cosine of the angle, because the force is going to decrease as the angle increases, because if you go to the extreme, it'll just fall. It's not going to stick. Oh, was that what you wanted? Oh, Arib, do you still want to say what you wanted to say?
Yeah, I wanted to mention that like the formula here, theta equals arctan y over x. It could have there's two possible answers. Like if your angles, if your vector's in like the first quadrant here, it's going to be this value, but it could also be 180 degrees plus this value if your vector's in the third quadrant, say. So like arctan of y over x, the angle could either be this or 180 degrees plus this. And you have to kind of like determine it based on the vector. So like this isn't the whole truth or whatever.
Well, almost. So let's look at the different quadrants. So if we look at the different quadrants, right, and we throw this angle, for example, into the third quadrant, you know, this will be our Rx, and Ry, sorry, and this will be our Rx. And yeah, what you're talking about is we want to measure the direction of this angle. So what is the angle? What is the direction of this vector? Does someone want to draw that direction on this graph? Like, what will the angle look like? Perfect. So that's what Ariba's talking about. Because what angle will the arctangent of Ry over Rx give us? It's being very quiet today. Not quite. Arctangent of Ry over Rx will give us this angle. Yeah, this one. Now, yeah, so you can either say it's going to be 180 plus that, or you can just say it's equal to minus that, because it'll be what's called a negative angle. Okay, so we've covered like components and different things that a vector has. And of course, obviously, these components don't necessarily have to be the absolute x-axis and the absolute y-axis. You can pick whatever basis you'd like, and you can describe these vectors with respect to literally any basis. So again, if you're on an incline, you know, and you're talking about this block on your incline, you know, this is your horizontal component and this is your vertical component, for example. And that doesn't necessarily have to be the absolute x and the absolute y. But we'll get to that later, like when we actually talk about physics. Just know now that you can split up any vector into their components, but fundamentally a vector has a magnitude and a direction. So now we get to the fun part. We talk about vector operations. Alvin, if you'd like to make a new page. By the way, if you guys have questions, please ask. Like, put a thumbs up or a check mark or raise your hand if you guys are like following everything I'm saying. Like, you guys got no questions. This is as I feared. Okay, I see 2 check marks. I see 3 hand raises. I see 4. Okay. Okay. So I see 4 thumbs up and I saw about 4 hand raises. Okay, Jeremy. So I asked, please raise your hand or put a thumbs up if you like have no questions about what I just talked about, like about what vectors have, like magnitude, direction, and components. Okay. Okay, so about half of you. Okay, well, we'll see based on problems, the true understanding of things. So now we talk about the fun part. We talk about vector operations. So vectors, can we add them? So let me write operations. So question 1, can we add them? Okay, I see some yeses. Yes, good question. Yes. Yes. Yes, sir. What? Okay. Oh, yes, sir. No, I'm not even gonna try to decipher that. Okay. So yes, the short answer is yes. The long answer is if the vectors are correctly oriented. So for example, can I add this vector and this vector? Yeah. Can I add this vector and that vector? Yeah. So technically speaking, yes, I can, but it would be much easier if the vector were here. So yeah, place them both at the same point and then you can add them. That's the long answer. Cool. So now, what does it mean to add a vector? What does it mean to add two vectors? Does someone want to try to guess what that means conceptually? What does it mean to add a vector? You add the components. Cool. So what do you mean by that? Okay, I see tail and head, direction and magnitude after both vectors are put on an object. Exactly. Cool. So let's try to understand what it means to add two vectors conceptually. So I'm going to describe a very simple physical setup. All right. We have a box. All right. And we have thrown it. We've thrown it at a certain, at like an angle theta up in the air. All right. We've enacted a force on it. And now it's flying through the air. What is the net force acting on that box? And in what direction is that net force acting? So for this, we need to add all of the vectors. So what we're going to talk about in the future is, there's this force acting at an angle theta. There's gravity acting down. And now we need to add them. And, sorry, this is a G. And, in the future, when we talk about even more complicated problems, there will be drag, which goes this way. So cool, we have three different vectors, three quantities. We need to find the net force. How do we do that? We add them. So I heard a lot of, I see tail, head to tail, find direction and magnitude. So what that means is we're going to try to construct a third vector which involves the other two vectors. So I see what's called head to tail attachment. So what that means here is we take if we have two vectors like this, we have vector A, we have vector B. This is A, this is B. We're going to take, for example, if we want to have A plus B, we're going to move the tail, the head of B. This is what's called the head, or sorry, is this the tail? I don't even remember anymore. Whatever. We move one part of B to the edge of A. I'm just gonna. My grandfather smoked his whole life. Okay, My explanation gave you cancer. Thanks for the subtle roast. Okay, so here. Yeah. Okay, yeah, I'm not crazy. This is the tail, and the other part is the head. So we take the tail of vector B, and we attach it to the head of vector A. So this is our new vector B. And this vector B is the same as this vector B because the magnitude is the same and the direction is the same. Cool. So now, when I describe A plus B, when I describe the vector A plus B, I'm describing the vector whose tail is at A and whose head is at B. This is A plus B. This vector. Can everybody can see that vector? I'm going to highlight it in yellow. This is our vector A plus B. So fundamentally, geometrically, that's what a vector is. Cool. What's its magnitude? Because it's not A plus B. Because if anything, if geometry has taught me anything, then by the triangle inequality, that is less than A plus B. So this is where components come in. We don't speak of Eric Kim. But here, we don't speak of Sue.Khan either. So if we describe A as AX and AY, by the way, this is the notation for vectors. We have like these little, what are they, angled brackets? That's, I think that's what they're called. Leon Maxon, not Maskin, Maxon, but here, anyway. And we have B equals BX, BY. How do we write out this vector sum A plus B in terms of AX, AY, and BX, BY? I'm gonna redraw the vector A and the vector B here, just so that you guys see it clearer. And I'm gonna notate what AX and AY are. So here's AX, here's BX, here's AY, and here is BY. So now, if I'm describing this vector, is B on the x-axis right now? No, the x-axis is this. This is our x-axis. I've moved B here to the head of A. So now, if I want to describe A plus B in terms of these components, what am I going to get? Shout it out, write it here. And I see Arib and Stephen have been participating a lot. So someone other than Stephen and Arib, write on the board, please. Okay, so Jeremy has written in the chat. I guess that's good enough. So AX plus BX, AY plus BY. Cool, because what's the horizontal component of this? It's this, which is, incidentally, AX plus BX. Now, what's the vertical component of this? Oh, it's this, which is, you guessed it, AY plus BY. So there we go. In terms of components, A plus B is the sum of their horizontal components and the sum of their vertical components. So now we understand conceptually what vector sum refers to. We understand how to construct it. This is what's called the triangle law, because we've created a triangle. So yeah, that's addition. Now, of course, the next question is, Alvin, please make a new slide. But can we subtract them? So can we subtract them? Can we subtract vectors in principle? Okay, Arib, I see that you're jumping the gun. Like, let's try to keep it slow. Can we subtract vectors? Yes, we can. And as Arib has pointed out, A plus B, or sorry, A minus B equals A plus negative B. Now, if we can do this with numbers, why can't we do this with vectors? The answer is we can. So what does it mean to negate a vector? If I have a vector A, what is negative A? Can somebody draw negative A? Like right here. Someone draw negative A. Oh my God.
Will you just inverse the direction of A?
Exactly. You
Okay.
invert the direction. So you just go this way, and there's your negative A. So yeah, negating a vector just means flipping its direction, because -1 equals cosine of 100 equals yes, cosine of 180. Up, multiply the angle. So -1. Yes, I'm not crazy. So yeah, negating an angle or negating a vector means flipping it. So if I want to do a minus b, well, we know that a plus a minus b, b plus a minus b equals a, right? And now we know how to set up this type of vector addition, right? So we have b, and then we have a minus b, and then we have a. So this is a, this is b, and this is a minus b. Cool. So can someone tell me now, based on what we've just done, how to construct a minus b using a and b? Oh, that should be highlighted. Anyone? No takers? So if we say a plus b, to construct a plus b, we go.
Sorry, can you repeat the question?
Sure. So when we're describing constructing vector a plus b from a and b, we go from the tail of a to the head of b. Now we've just constructed a minus b using summation because we know that b plus a minus b equals a. So, okay, Mohammed, that's correct in terms of components. Now I'm asking for just the geometric interpretation. If the geometric interpretation of vector addition is going from the tail of one vector to the head of another for addition, what's the geometric interpretation for subtracting one vector from another? You want to say that in words?
Would you start the tail and then like go the opposite direction of B? I mean, you would start the end of A and then you would go in the opposite direction of what B originally was.
Well, you see here how we started at B?
Yeah.
So yeah, if you amend your statement and we say we go from the other vector, we go from the head of the other vector to the head of the first vector, then yes, there's your interpretation for subtraction. Does that kind of make sense?
Also, something that's pretty interesting, or a way you can think about it, I guess, is if you look at b and a minus b, then you get that b plus a minus b is equal to a. And if you look at it geometrically, then that's indeed true because you're appending the tail of a minus b to the head of b, and then the resultant vector that you get after adding them is going to be just a. And also, if we look at the, I'm just going to erase the blue lines over here. If we have two vectors, b and a, and then, you know, we copy a to the head of b, and we copy b to the head of a like that, then this diagonal, this makes a parallelogram because these are the same vectors, so they have the same orientation, and so does b. So this diagonal over here, this is going to be the sum. So this is going to be a plus b, right? But the other diagonal is going to be a minus b. So, you know, you have like all the values that you need for addition and subtraction just within one parallelogram, which is going to be the b and a, which are the ones that you're working with, the long diagonal, and the shorter diagonal, which is going to be a plus b and a minus b. And I just think that's pretty interesting.
Yeah. So Alvin hit it exactly because we derived the subtraction vector geometrically using addition. So what Alvin has illustrated here is what we call the parallelogram law. And that's how we derive subtraction. So yeah, you can do it that way, you can do it any other way. Just geometrically speaking, if you're subtracting one vector from another, you're going from the head of the vector you're subtracting from, you go from the head of the vector you're subtracting to the head of the vector you're subtracting from. So if I'm doing a minus b, I go from the head of b to the head of a. There's geometrically what it is. So now let's derive it mathematically, algebraically. So if I have b here, ooh, it's not letting me draw again. Beautiful. Okay, if I have, this is my b, this is my a minus b. Can everybody see this? I'm a little too lazy to change the color. And this is a. You know, this here is my ax, and this here is my bx, right? In the same way that this whole thing is ay, and this thing is by. So if I'm looking at the components of this vector, I'm looking at this component for the horizontal and this component for the vertical. Well, this is obviously ax minus bx, and this is ay minus by. And there's your explanation for why you can just subtract, excuse me, the components. Ax minus bx, ay minus by. So these are the most basic things you can do. You can add them, you can subtract them. Please, so I found that putting a thumbs up means I have to scroll through the participant window. So just everyone raise your hand if you totally get the material. If you don't get the material, do not put your hand up, and we will address any question you may have. Yeah, so in any case, in case anybody didn't catch, this is notation for components. When we notate components, we put them in these triangle brackets. Okay, so I see, did anybody put their hand down, or did somebody forget to put their hand up? Just keep your hands up if you totally understand all the material. Everybody who understands the material, put your hand up. Arib, I meant in the participant window, but thanks. Hi. Okay, so I see 4 people do not understand. So you guys have any specific questions, or are you guys just forgetting to put your hands up? Ivan, Najia, Richard, Tracy. If you got questions, ask them now. Or ask them during our office hours session on Saturday at 4:30. Preferably now, so that we can clear up any issues right now. No? Nothing? Okie dokes. So now we're going to get into the now we're going to get into the just 2 more operations that you can do with vectors, one of which I'm going to cover a bit more extensively than the other, because the other will pop up later in physics. But actually, I will quickly mention what a unit vector is. Arib, that is a good point. Can anybody tell me what a unit vector is? So I'll ask a simpler question. Actually, oh no, there we go. Okay, so a vector with a magnitude of 1 unit. Exactly. The same way that a unit circle is a circle with a radius of 1, a unit vector is a vector with a magnitude of 1. Perfect. That's just useful to know, because sometimes you can deal with unit vectors. You can add them to, you can add things to get to unit vectors. Yeah, they're typically notated with a hat. Exactly. So many of you have probably either seen or heard of I hat and j hat. These are unit vectors that refer to direction. I hat and j hat usually define your reference frame. Yeah, exactly. Jeremy, you hit it. So these are used to set your coordinate basis, because if you are dealing with this coordinate basis, well, then your I hat is x, is the x-axis, and your j hat is the y-axis. But if you're dealing, for example, let me just use a different color. If you're dealing with this reference frame, well, now your I hat and your j, this is your I hat, and this is your j hat. Because if you multiply by I hat, or if you multiply by j hat, what happens is the magnitude isn't changing, but the direction is. So if you multiply by I hat, you multiply by j hat, you're basically shifting your reference frame. That's why we usually see vectors denoted not just, you don't see just like regular these components. You see something like something I hat plus something j hat. And that means you're referring to this reference and that reference. So that's what unit vectors are used for. It's just basic. So now let's talk about what's called a dot product and a cross product. Because can we multiply vectors? Okay, so I'm going to quickly explain what a dot product is, and then we should take 10 minutes because I think I've been talking a lot. So, okay, the short answer, the really short answer is yes. The slightly more general answer is kind of. Because what does it mean to multiply a vector? What am I multiplying by? Am I multiplying by the magnitude? Am I multiplying by the direction? So the answer to can you multiply vectors is kind of. Well, okay, so I see Arif's talking about scalar products and vector products. But we're going to use dot product and cross product a bit more simply. So dot products and cross products are how we multiply vectors, because multiplication in algebra is repeated addition. But multiplication with vectors is not repeatedly adding vectors. If you're doing A times B, you're not adding B to itself A times, because A is not a number, A is a vector. A has a direction too. So let's talk about what it means. So the first thing that I want to quickly just bring up is what's called a dot product. So a dot product is what we usually mean in physics when we say multiply vectors. So it's denoted A dot B, and that's our dot product. So our dot product describes something a bit unusual. What a dot product describes is basically how much of an effect one vector has on another. So the way the dot product is defined is A dot B equals the magnitude of A times the magnitude of B times the cosine of the angle between them. So if this is A, this is B, and this is theta, that's what A dot B is. A dot B is basically describing like the impact or the effect that A has on B. It's really weird. Conceptually, dot products are really confusing, but essentially, that's our way of faux multiplication. So does somebody want to tell me what dot products are purely algebraically, not using cosines? I don't like angles. What if I don't know the angle? How can I write out the dot product of a vector? Okay, so I see ax bx plus ay by. Cool. So why? Okay, let's look at our formula. Magnitude of A is the square root of ax squared plus ay squared. Magnitude of B is the square root of bx squared plus by squared. So, and cosine theta equals, excuse me, what does cosine of theta equal to? Can somebody tell me what the cosine of this angle is equal to? Well, let's describe the components. So,
I was gonna say maybe AY over BX. But that's only assuming that like B is a flat horizontal.
well, not necessarily, because if B is not flat, then the angle is still the same, right? If we shift our reference frame, if we move,
You're right.
we
It's
looking
the
like this,
reference frame.
yeah, exactly. So in order to compute that angle, we don't have to rotate the angle, because if we rotate the angle, then we're changing it. What we can do is we can just tilt our head. And when we tilt our head, we change our reference frame. And then this remains the exact same. This component is still the same. So cosine of this angle is the adjacent over the hypotenuse, right? Which is the magnitude of B over the magnitude of A, equals B over A. So then what happens if I multiply square root of, if I multiply, let me just make sure I did this correctly. Yeah. What happens if I multiply this? So I get it's A times B over A, which is equal to B squared. Beautiful. I may have done this the wrong way, but yeah, you might have to just ignore me completely because I think I messed something up. Alvin, if you'd like to chime in, feel free. If you'd like me to just stop talking, go ahead.
All right, so we want to find the cosine of the angle theta, right? I'm also kind of winging this, but
So I also winged this derivation. Feel free to just memorize what the dot product means. You don't have to remember this derivation. This is the least important part of a dot product.
okay, so actually, so this is going to be the y component of A, right? And this is actually going to be the x component of A. So actually, like both the things that are involved in the cosine are related to the to A, right? So I'm just gonna try that out. If this goes wrong, you guys can just go to Google. So AB times the cosine of theta, right? So cosine of theta is then gonna be equal to A sub x over the magnitude of A, right? So that means this is going to be equal to magnitude of A times the magnitude of B times A sub x over the magnitude of A. And then now these cancel out. Now, like, what is the magnitude of B? So the magnitude of B is equal to the square root of bx squared plus by squared. And then we can multiply that with a sub x, which is the square root of a sub x squared, right? And then now what we get is the square root of by the distributive property of multiplication inside, and we can also distribute multiplication inside of square roots. We get this is equal to a sub x, b sub x squared plus a sub x, b sub y squared. All right, now let's move to a new page. So what do we have? So ax bx and then ax by. All right. So let's just verify. Like, is this actually equal to ax bx plus ay by? All right, so what happens when we square this? When we square this, we get ax bx squared plus ay by ax bx plus the second part squared, which is ay by squared. And is this equal to ax bx squared plus ax by squared? Now, let's kind of go back to our drawing. Right, so originally we had the top vector being A and the bottom vector being B. Right.
Alvin, I think you might have screwed the pooch. I think it's ax yeah, I don't know where you got ay in this. Are you squaring this first?
Yeah, I'm squaring the. I switched the left and right sides.
I see. Okay, just make a note. RH and LH have switched. I said screwed the pooch, Areep.
All right. So,
I've started it.
Well, actually, I might have also messed this up.
You know what? You know what? Just gonna. All right. So I think we all need a break. So actually, let's take a break until 6, and then I'll give you guys a brief overview of
the derivation. Hold on.
You can remember the derivation. Everybody else take 10.
Yes, take 10 minutes, guys.
If we remember the derivation, we'll tell you. But for now, A dot B equals AB cosine theta equals AX BX, sorry, plus AY BY. My God, that's embarrassing.
All right, take 10 minutes.
Just be back at 5. Yeah, be back at 5. Oh my God.
6, Andrew, not 5.
Oh, sorry. Oh, my bad. At 6. I keep forgetting it's 5:40. Yeah, be back at 6. Sorry. We do, but we didn't derive the dot product. We stated it. I just sort of decided to derive it for literally no reason. So we'll probably, since we invested so much time trying to remember a derivation we learned 2.5 years ago, we'll include it in the notes because it would be remiss. Put it as a p-set question. Oh yeah, would you guys like to derive the dot product? Finish the proof. Oh my god. All right, see everyone at 6.
All right. It's 6 o'clock. So we're just gonna carry on for like half an hour more, and yeah, so we're just gonna be finishing vectors. So if you guys are back and present, could you please raise your hand?
And while everybody's raising their hand, I know I've said this before, and I feel a little, like a broken record with this, but let's try for everyone in the future, at least in the coming meets, hopefully for this last half hour, let's try to have our cameras on. The reason I ask for this is, first of all, like, it's much easier to see if you guys are like looking and understanding if we can look at a face. Otherwise, it also just feels like we're just talking to names, and we're trying to simulate a classroom experience here. So, like, again, if you guys really don't feel comfortable, or if you guys physically cannot, that's understandable. That's completely fine. But otherwise, it would be desirable if you guys could turn on your cameras, just so that we're talking to actual people here, to make it just more person to person. But whatever is possible, I guess, for people.
All right, so we're just gonna be tagging this as an extra problem on the P set, but then I guess so it would just be to show that given vector A is equal to a sub x, a sub y, or you can rename these if you want, but and given vector B is equal to b sub x, b sub y, then show that A dot B, or show that these two definitions of the dot product are the same. So AX times BX plus AY times BY is equal to A, the magnitude of A times the magnitude of B times the cosine of the included angle. And so as a hint, I guess, to start off, the derivation uses the law of cosines, okay, which states that in any given triangle with angle theta here and side lengths of A, B, and C, that C squared is equal to A squared plus B squared minus 2AB. I'm sorry this is tilted, by the way, but C squared equals A squared plus B squared minus 2AB cosine of theta. So the derivation of this property, like the first step is going to use the law of cosines. So yeah, it's going to be an extra problem on the P set. And oh yeah,
Alvin and I were too embarrassed
I mean,
let this slide.
I re-derived it in that 10 minutes. But,
Yeah, same.
but I guess since we mentioned this already, it's going to be another problem. Oh yeah, so with these presets, by the way, you do as many as you can. All right, and there's gonna be some challenging problems on there, and these are gonna be for discussion in the next session. But
And the problem count should go from 5 to 7. So, I mean, it would be ideal, like, a good indicator that you are really understanding the material is if you can solve at least 4 of those problems. If you can solve at least 4 out of the 7 problems that we give, that means you are understanding the material. With a little bit of practice, with a little bit of more drilling, you'll be able to solve all 7. If you can ace all 7 problems consistently, then you're getting the material. If you can ace it in under an hour, then go to Team Einstein. But yeah, is the P set the same one as we have to hand in? Yes, we called it. I'm not sure if we called it assignment or homework, but yeah, those are the problem sets that we're talking about.
Solutions to the P set in Google Classroom by Monday. So yeah. So I guess now we explored some definitions of the dot product. Now we can move on to the cross product, yes.
I'm gonna draw something, and it's either going to trigger you or confuse you, depending on how familiar you are with the dot product.
Steven, do you have a question or is your hand just up from before? All right.
Oh yeah, it's from before.
Mhm.
Okay, so if you're triggered, all right, yeah, good, Arif, this is the right-hand rule. If you're triggered, good, this will trigger you because you're in a physics Olympiad, in like F equals MA and USUFO, you're gonna see people doing this. And during physics exams, you're gonna see people doing this. No, they're not going insane and they are not suffering a seizure. They are trying to determine in which direction the cross product goes. Put simply, the dot product is what Arib called a scalar product. So what that means is the result that you get from a dot product is a scalar, it's a number. A dot B will give you a number. A dot B equals some sort of X, where X is then defined as AX, BX plus AY, BY. It's a number. Now, the cross product of A cross B, is going to be a vector, some sort of vector C. Now, there are plenty of ways to describe what a cross product is. There's the matrix definition, which is icky. There's the AB sine theta definition, which looks like a dot product, but isn't. And then there's the weird component derivation. Yeah, so put simply, most of the time, it'll be helpful to think of A cross B, or the magnitude of A cross B, as, I don't know why my thing is so slow right now, but AB sine theta. What is happening? I don't know why this is completely illegible. My tablet isn't dying. So let me write this again. AB sine theta. Okay, I don't know what's going on, but my tablet seems to not want to work.
Do you want me to scribe and
Go ahead, please. Until my tablet stops being stupid. Scribe for me. Oh.
All right, so what's going on over here is A dot B is always going to be a number,
Or what we call a scalar.
what we call a scalar, yeah. And I don't know why my thing's tilted.
Mine's also tilted.
Cross B is always going to be a vector. And this is why we'll sometimes call the dot product the scalar product and the cross product the vector product.
Yeah. So again, we refer to the magnitude of A cross B as AB sine theta. Now that's the formula that's going to be useful when we talk about torque, when we talk about angular momentum, when we talk about all of those things that involve cross products. But don't get confused. The value of A dot B equals AB cosine theta. A cross B does not equal AB sine theta. The magnitude of A cross B equals AB sine theta. The magnitude of that vector is what we're talking about when we talk about cross products. But really, cross products, we're producing a vector. That's why we do this. And the cross product, the reason you see this is because the cross product is perpendicular to the plane on which your two vectors lie. So if you have vector A and vector B on one plane, then A cross B is going to be perpendicular to that plane. That's where we get this from. Now, you're going to see a lot of different symbols like into the page, out of the page, left, right, up, down, all that crap. So that's referring to the direction of A cross B with respect to A and B. So, Alvin, you want to sort of give the table, into the page, out of the page, all that crap?
Yeah, okay, so I might have forgotten a little bit of the symbology, but so let's just say you have two vectors that are on the plane that the page is in, right? So then if a vector is pointing out of the screen at you, then I think it's denoted by like an X. Is that right, Andrew?
That's into the page, yes.
Okay, so X is into the page. Then that means a circle with a dot is out of the page, right? And then a circle with an X, this means it's into the page. So this is out of page, and into the page. And then we're going to be using these two symbols. Yeah, we're going to be sort of using these two symbols. So into page. So now how do we determine, okay, so we have the magnitude of A cross B figured out, right? The magnitude of A cross B is equal to the magnitude of A times the magnitude of B times the sine of the included angle. But how do we tell which side it is gonna go in? So here's what we do. So we take our coordinate system, which is gonna be, the coordinate system on our page, right? And, so that means this is gonna be the Y direction and this is gonna be the X direction. So now let's just have two random vectors. So who wants to, so people in the chat, give me like two numbers as angle measures from 0 to 360 for the vectors to point in.
15 and 74. Oh my God.
Well, hopefully they're not in the same quadrant. So
Yeah, let's try to.
I'm gonna use 54 and 109. So 54 is about like here.
Close enough.
And 109
Is here, let me draw it. Or go ahead.
109 is about here. Okay. So we consider two situations. The first situation is A cross B. And the second situation is B cross A. So here's how the right hand rule works. Your right hand is actually going to tell you whether or not it points out of the page or into the page. So like, can you guys all see my right hand over here? Yes? No? That is just convention. Yeah, it is. Actually, the right hand rule determines the behavior of a lot of physical laws. So it should be more than just convention. But all right, so like everyone hold your right hand up. So now what you do is, let's look at the first case, which is A cross B, right? So what you do is, so let's line our fingers up with A. And because my camera is inverted, I'm actually going to use my left hand, but you should use your right hand. So A goes in this direction, right? And then you want to curl your fingers in the direction of the B vector. So then the B vector is to the left of the A vector. So that's why I curl my fingers this way. Right? I curl my fingers this way. And now take note of where your thumb is pointing. So is your thumb pointing at your face or into the screen? So you line your fingers up with the vector A, and then you curl your fingers towards the direction of the vector B. So where is your thumb pointing? Anyone? Thumb is pointing at the screen.
You mean away from the screen?
Away or towards the screen? That's not what I got.
Okay, Arib, you say to you, so it points away from the screen,
Wait,
right?
it's supposed to point, okay, because, is my camera inverted? It's actually not inverted. Yeah, okay, so that means A is this way, right? And you want to curl it towards B. So it goes, you curl your fingers that way towards B. Yeah, you're not supposed to curl your thumb. Keep your thumb straight, right? And then your thumb should be pointing towards you, right? Is everyone's thumb pointing towards themselves? Hopefully it is. So that's how we know that A cross B is going to be pointing out of the page into your face, right? So like, what about the opposite situation? Now you want to align your fingers with B and then curl them towards A, right? So then you curl it to the right like that. So now in this situation, where is your thumb pointing? Into the screen or like to your face?
It's a shame we can't see you guys, but we hope you're doing it.
You know, it's really a marvel when the entire physics class starts to mess with their hand in weird.
Hands, and they do this, and oh, it's adorable.
Anyways, yeah, so like in this situation, for B cross A, it's gonna point into the page, right? Or in this case, into the screen. So yeah, and then the direction of the resultant vector of the cross product is always gonna be perpendicular to the plane, which is defined by B and A. And you know, B and A always can define a plane because it's basically a triangle, right? If you consider the endpoints and the tail, it's 3 points, triangle, triangle determines a plane, and C is always going to be perpendicular. But to determine which way it's perpendicular, you can use the right-hand rule, right? So A cross B points out of the page, and B cross A points into the page. Okay, so, and they all have the same magnitude, right? So that means the cross product is actually not commutative, which means that A cross B is not equal to B cross A because they're pointing in different directions. So what they actually are, they're called anti-parallel, which is what you call vectors that have that point in opposite directions. So for example, like this vector and this vector, these are anti-parallel vectors. And because anti-parallelism just says that it's negative, we can just denote A cross B as the negative of B cross A. Right, so
It's inversely commutative, or
it's inversely commutative.
I might have just completely made that term up, but I'm pretty sure that's what it is. Yeah, but the dot product is commutative because the dot product is just a number. But the cross product, because it's a vector, and you have to take into account the direction of the vector because it could either be pointed towards you or away from you, that's why we have the negative sign. But the magnitude of the cross product will always be the same. Remember that.
Okay, so now I'm just gonna give you guys another formal definition without a proof because I actually don't know the proof for this one. But so here's like so when you're actually dealing with maybe 3-dimensional vectors, then just, you know, just determining the plane that is determined by the vectors and whether or not you know, whether or not the resultant vector actually points in this direction or this direction, that's like pretty hard. So I'm gonna give you guys a formula for determining what the cross product is gonna be, just in terms of the algebra and the coordinates of the vectors. So if you guys know linear algebra, then if you guys know linear algebra, this is gonna be really, this is gonna click for you. But then if you don't know linear algebra, I don't know the proof, I'm sorry. And
if you're not a second-year graduate student, just assume this is a correct. If you are, if you happen to be a second-year grad student, give us the proof. But yeah, again, just as a disclaimer, while Alvin writes this, this is so unnecessary for the physics that you have to learn that this is just a fun thing to know. You don't need to know this. It is a fun thing that you just can know. The proof for this is not that bad. If you really want to find the proof, you can talk to me after office hours. But like,
oh yeah, by the way, office hours are now on Saturday at 4:30. So if you have trouble, if you have any troubles with the P set or you have anything to ask, you know, you can just come to us during that time. All right, so so this is what's called a matrix, right? It's just basically a 2-dimensional array of numbers, and the top row is going to be our unit vectors. So I is the unit vector pointing in the x direction, j is the unit vector pointing in the y direction, and k is the unit vector pointing in the z direction. So and then A cross B is going to be the determinant of this matrix. And it's actually going to result in a vector and not
the magnitude is the determinant.
Yeah.
The
Um,
actual A cross B is that matrix, because this matrix defines a vector.
right. So yeah, again, you guys don't have to know why, but the the determinant of this vector, it comes down to I hat times the determinant of AZ. So yeah, this is just a complex or a compact way of sort of defining BZ plus J hat times AZ AX BZ plus K hat times the determinant of AX AY BX BY. Right, and then so by doing this, and by the way, so AX is the x component of the A vector, AY is the Y component of the A vector, and AZ is the Z component of the Z vector. And now to calculate a two-dimensional determinant, all you need to do,
Isn't it just AXAZ, BXBZ? Did you flip it by accident? Or
where? For
here?
J?
Yeah. Or am I confusing things?
Yeah, I think I did, sorry. So we got X times Z.
I color coded it as best as I could. Again, you don't need to know this. This is linear algebra. This is not high school physics. This is just a thing for cross products. All you need to know is that in regular physics, in mechanics, the only formula that matters is the magnitude of A cross B equals AB sine theta. In E&M, you need to remember the directions, because you're going to be doing that with electric and magnetic fields. You're going to be working with directions. But right now, A cross B equals AB sine theta, no questions asked.
So I think this is actually more important for the future, but I think I have seen an F equals MA question regarding a cross product
Really?
of two vectors. I'm not sure though. Anyways, so for a two-dimensional vector or a two-dimensional matrix or a 2x2 matrix, the calculating the determinant is pretty easy, right? So it's just A times D minus B times C. And then, you do this operation to all like I hat, J hat, and K hat, and then you get all three components of A cross B, which tells you exactly what vector A cross B is. So yeah, and then, this is going to be a long formula if I were to write out every single part, but then, if you're just going to remember this, you just remember this formula, and, and you know how to decompose a 3x3 matrix and find its determinant, then, this is going to just be, it's a lot of information that can be encoded into like a single little piece.
So in summary, A cross B equals AB sine theta, done.
Yeah. And
that's what you need to know for high school physics.
Equivalent to the vector with a magnitude of AB sine theta and the direction being.
I think your second term in that cross product thing is wrong. Shouldn't it be AZ AX, not
That's
AX
That's
AZ?
what I had before. Actually, no. It's this is.
I think you might have. It should have been. I think it should be AXAZ. Or am I crazy? Are you supposed to flip it?
Well, from the component formula, I know the second term is AZ BX minus minus BZ. Wait, AZ BX minus AX BZ.
Okay. Well. Okay. We have this.
Yeah, it's C then X. I think that's correct.
Yeah, my mistake. I think I accidentally flipped it. Okay. Anyway, this is just, again, this is ridiculously advanced stuff that you guys really don't need to know. Like, really, all that matters is oh my God. Ignoring the mess I made. What the hell? Sorry, I'm just gonna put down my pen. A cross B equals AB sine theta. And that about wraps it up with vectors. So I thought we were gonna have time to cover a very basic introduction to calculus, but unless I speak at like 150 words per minute and I really talk quickly and I don't stop for anybody to do anything, then no, we're not gonna cover
I
like
think we
fundamentals
can
of
stop
calculus.
on a simple problem.
Yeah. So you found a proof. Cool.
Well, I don't think we're going to go over it.
We're not gonna go over the proofs. So again, just to summarize, vectors are a very important thing in physics. They allow us to picture and understand things. When we cover free body diagrams in like the next class or maybe the class after that, you're going to see that we use almost exclusively vectors because, you know, how do we describe a force? You know, a force has a magnitude, a certain amount of newtons, and it's being exerted in some direction. We can denote that as a vector. The force of gravity acts downwards at a certain force, Fg, which is the mass times the gravitational acceleration, mg. So we're going to use vectors everywhere. Now you know how to add them, and adding becomes useful when you need to find the net force, the net vector. Subtracting is useful when you're talking about opposing vectors. So for example, you know, this thing is flying in this direction, but the problem is there's a force of friction acting in this direction, and you need to subtract that force to find exactly how much, you know, it's flying in that direction. So we know how to add, we know how to subtract. The dot product multiplies them and gives us a number, and the cross product gives us a vector. So those are the biggest things. And you can always split up vectors into components, and components are very useful when dealing with different reference frames. So if you're at an incline, and you can't work with this basis, but you can work with this basis, multiply by the cosine or the sine of the angle, depending on which component you're working with. And that will automatically shift it. So those are the big important things you need to know. And here is our problem. We're given this vector, A is 2, -3, B is 5, 1, and we want you to find A plus B, A minus B, and A dot B. You
Yes.
guys got...
Just send me the answer in a PM, and then you guys are free to go.
Or you can PM me, whoever you like. For the next lecture, you guys should plan out your lecture beforehand instead of just winging it.
We didn't have the derivation in our lecture notes.
Yeah, we had literally everything other than the derivations in our lecture notes. So we winged the derivation. And you can tell as soon as we winged the derivation, we completely lost everything. But don't worry, we're starting with actual physics next week. We're doing kinematics, and that's going to be our actual dive into physics. And again, I just want to reiterate, while you guys are working on this problem, it's very important to stay on top of the material we're learning. That means ask questions if you have them. We don't bite. We understand that we are human. We are not teachers. We don't have certified degrees. If we talk too quickly, or if we skim over something that's not obvious to you, ask us. We'll go over it slowly. We'll try to answer every question you give us. And if it's not during lecture, ask us, you know, either during office hours when you know we're available on Zoom, or ask us on Discord, or email us, or post in the classroom. Any questions, we'll answer them. Because right now, especially, if you start falling behind, the rest of physics is going to be a complete crapshoot. Because if vectors are complicated, which they are, you know, you have to understand vectors. If you don't, then breaking down a physics problem into forces is going to be very difficult. And then solving a problem involving forces is going to be near impossible, because visualization is key in physics. So especially now, but definitely at any moment, if you guys have any questions, ask us. If you guys are working on the problem set, do the problem set before the due date. Like really, that gives us enough time to look it over and give you personalized feedback, and that gives you time to read over our feedback and learn from it. So yeah, come to office hours, email us, text us, whatever, as long as it's not at 2 in the morning. But maybe it's 2 in the morning. I'm a senior and I'm applying to colleges, so I'm probably awake at 2 in the morning anyway. Point is, really, ask us.
Right.
Our goal here is not to get through it as quickly as possible. It's to actually teach you guys something. So if you guys have been PMing Alvin or me the answers, if they're correct, we'll let you know. And if it's correct, feel free to go. if it's not, like, we'll let you know. Okay, so, okay, let's see.
All right, so like most of the stuff, so the lecture notes for this lecture is actually just, most of what we said is just in the math sheet, right? The math review sheet that we sent out a while ago. So yeah, you guys can check that out if you want to, refresh yourself on anything. Also, this meeting is being recorded. So we're going to be sharing this recording to the Google Classroom and also all of our slides.
And I will probably sometime closer to the end of the week update the physics team website to have the PSET, the lecture notes, and the recorded lecture available there.
Mm-hmm.
In answer to Arib, well, I plan on majoring in physics. I don't know about Alvin.
It's a possibility.
Oh, by the way, have I been too loud? Am I talking too loud? Because if I'm yelling at you guys, I'm sorry.
You're fine.
All right. Cool. So again, if you guys got it correct, feel free to leave. We'll see you in office hours, hopefully. If not in office hours, then next Tuesday. Please, again, any questions, email us, ask us, write on Discord, hop onto office hours on Saturday. See you guys then.
See ya.
See you.
Mm-hmm. I am not. I pretend like I am, but I'm not. Arib, did you send your answers to the 3 questions?
He
Cool.
sent it to me.
Awesome.
Yeah, so like, if you sent in your answers, feel free to leave.
Yeah, we won't keep you any longer.
Mm-hmm. Next week, we're going to be doing 1D kinematics. So Richard, Leah, and did Leah send me?
Leah sent it to me. So Leah, try, I'm writing this in a comment, but consider the dot product in terms of components, since we don't have the angles. And calculating the magnitude is just extra work. You already have the components. Consider it in component form.
Yeah, so like it really depends on what you're given. So you want to find it the easier way. Right, so if you're given components, for example, you just want to multiply them, and that's going to be easier. What about Richard and Tracy?